Hello, Adam Creek here, and this is my report for the application of the Markov chain Monte Carlo sampling and its use for Bayesian models in space or astronomy. The following agenda items will be covered in the presentation. MCMC sampling is a class of algorithms that is used to sample from a probability distribution when direct sampling is difficult, and this is often the case in the space domain or astronomy. MCMC methods have two components: the Markov chain, which is a sequence of random variables where the distribution of each variable depends on the state of the previous one. And the second is the Monte Carlo element, which relies on repeated random sampling to obtain numeric results. And the core idea of using this randomness to solve problems that may be deterministic in nature. By combining these into the MCMC sampling, we can effectively approximate the posterior distribution of parameters in the Bayesian analysis, even when the distribution is complex and high dimensional. This also allows for robust inference and decision making based on the observed data and prior knowledge. The research paper has a focus on developing a framework for parameter estimation from black hole images, which utilizes MCMC sampling within the context of a Bayesian model. Here is the research paper that's been referenced in the report. The researchers used an open source Python library to develop the framework with input from VLBI data. The parameter estimation of the posterior distribution follows the Bayes theorem, which is the product of the prior distribution and the likelihood function. The framework takes user input, including model selection, starting parameters, and defining priors. Then the MCMC ensemble sampler will generate a number of synthetic samples to run to a point to which the prior distributions converge to show reliable sampling. And this was evidenced by the trace and autocorrelation plots provided in the report. Some of the pros and cons identified in the paper include: the framework itself is quite flexible and handles both simple and complex models. It also can accommodate multiple likelihood functions and combines the computational power of MCMC sampling to estimate the posterior distribution. However, the framework is computationally intense, taking over 400 core hours to complete, and it is also limited to visibly amplitudes and requires real data validation. Recommendations for improvement include expanding the model to accommodate other models, such as the MG ring model for geometric modeling, and also SMBH binary capabilities, which is increasingly becoming an area of focus, that is supermassive black hole binaries. Medical imaging is a domain which could benefit from the use of MCMC sampling in a Bayesian neural networks, and it can enhance the accuracy of image classification. The Galfray framework could be used to benefit in this environment. And in terms of data input, this would be the use of medical scans, which would be labeled and classified. And in terms of priors, that would be referring to specialist domain knowledge, previous studies, which could account for bias, weights, and prior beliefs. Thank you. That concludes my presentation.